Okay, so I thought I'd quickly go through the Bebras challenge with you guys, and we can go through exactly the thinking behind answering some of these questions. So, first question we have: Taro is planning an animation of a face that is made from a sequence of pictures. To make the animation run smoothly, only one feature of the face should change from one picture to the next. Unfortunately, the pictures got mixed up. Now Taro must find the correct order again. Luckily, he knows which picture is last. Put the pictures in the correct order by dragging them into the squares. So there's two ways I can do this. The first one is I can work backwards, or the other option is I can work from the front. So I'd need to find which other animal or picture only has one feature different to this one, which is a little bit tricky to see straight away. But what I can see straight away is that this is the only one with huge ears. This one doesn't have huge ears, so I will drag this one to this side. Now I can see only one of these also has red whiskers, so that would obviously go there. Again, like I mentioned earlier on, I can work from the back again, but however, I can see straight away this is the only one with a small nose. These two have small, this one has big. So let's move that over there. And again, this one is looking a little bit sad. This one happy, happy, sad. So we know sad goes here, happy goes there. Animal competition. The beavers and dogs had a competition. In total, 9 animals took part. The 9 participants had the following scores: 1, 2, 2, 3, 4, 5, 5, 6, 7. No dog scored more than any beaver. So we know that the dogs are on the left hand side, the beavers on the right hand side. One dog tied with the beaver. Okay, so we only have 2 pairs, so the 2, 2 and the 5, 5. So we know that one of them would be a dog and a beaver. There were also 2 other dogs that tied with each other. So we know the dogs also tied. So that means the 2, 2 would have been the dogs, and the 5 would mean that one was a dog, one a beaver. So we can assume straight away that the 3 on this side were beavers, and the 3 on this side were dogs. And as we can see, there are 6 there. Okay, so the abacus. A number is represented on a Chinese abacus by the position of its beads. The value of a bead on the top part is 5. The value of a bead on the bottom part is 1. The abacus is reset to 0 by pushing the beads away from the center. To represent the number 1746,503, the appropriate beads are moved towards the center of the abacus. So the abacus is reset to 0 by pushing the beads away from the center. So as we can see, anything like this would represent a 0. Anything on the top line would be a 5, and would simply add the units to it. So similar to what we've been doing in binary with base 10, we're just using 5s and 1s on this time. Okay, so what number does the following abacus represent? So we would have a 5 at the top and 2 underneath. That would obviously be a 7, and we can see how that matches up with this one here, just to ensure we're correct. We have nothing in the middle there, similar to the zeros. There we go. That would be a 1, 4, 5, 6, 7, 8, 3, and a 1. So we can save that. Okay, let's go into the animals. 6 animals need to be put in 6 pens. An animal cannot be in a pen that shares a fence with an animal that eats it. The arrows in the diagram on the right show which animals eat each other. So frogs and chickens eat worms. Wolves eat sheep and chickens. Foxes eat chickens. Drag the animals below to the correct pens so that none of the animals get eaten. There may be more than one correct answer. Don't forget to press save. So the first thing I'll look at is which animals are only sort of eaten or eating one other animal. So that's the fox and the frog. So if I look at the maze, I can see that this cell here has 5 other animals sharing the same wall. This one here has the same 1, 2, 3, 4, 5. So it would mean that one of the ones which only shares with, or which only can eat or is eaten by one animal, would go into one of the 2 there. So the frog being one of them, I will pop the frog over here. And the one, So the frog eats the worm, so the worm should not be touching or sharing a wall with the frog. So we've got the worm there. The chicken, again, should not be with the worm, so we can move the chicken not to any of these two, but to one of these two. Okay, so I need to ensure now that the fox and the wolf are not touching or not sharing a wall with the chicken. So let's start with the fox. Let's put the fox there. Fox has no interaction with the frog or the worm, and the wolf will also go there. The wolf has no interaction with the fox or the frog, and last but not least, we've got the sheep there. The sheep only interacts with the fox, sorry, the wolf, and it's not touching there either. Okay, so we can save that and move on. Help Smiley get through the arrow maze and back to his house. When standing on a square with an arrow, Smiley must move to the next square by following the direction of the arrow. Smiley can start from either yellow square with a start flag, so he can either start from one of these two. At the moment, it is impossible for Smiley to reach his house. Your task is to change the direction of only one arrow so that Smiley can follow the arrows to his house. So he must start from this arrow or this arrow. If he was to start from here, he would go straight there, straight back, so that would not work. If I was to change this, again, that would be coming back to him, so none of these two would be the ones to change, or this one wouldn't be the one to change anyway. If I was to move this, to rotate this, I could bring that down there, but that is then simply coming back round there. Okay, so we know that these two aren't ones to change. And so we know that he cannot start from here. So we know that he will start from this square, he will come here, down, and again back here. So we need to change something in this so that he gets out of this loop. If he comes here, if we rotate that back up, again, he will come back there. If I was to rotate this into this direction, again, he's going to get stuck. So it would not be this one. If we rotate this one to go down, again, constantly rotate back, upwards, rotate back to the right hand side, he would then go down into the house there. So I would know, basically by trial and error, I worked out that this one was the correct arrow to change. Okay, so Lena is very happy to discover an ancient table of letters and symbols. This will help her decode the ancient message she found last year. Lena now knows that letters have symbols. Each letter symbol is made from their column and row symbol. The letter H is made like this. So we have this pineapple looking shape with a 3-lined circle inside it, which would make the letter H. Lena can now decode this message. So we have this sort of calendar notebook looking shape, which would mean one of these with 3 lines inside it, which mean we start off with an L. Now, do I need to translate this whole message? I already know straight away that it's either love water or love my son. So what I can do is I can hop over to the W or the M and see which one of these it works out to be. In fact, I'm going to head over to the last letter, in this case, which is again this calendar looking shape with the power button, which is an R, so it must be love water. And just for the sake of verification, I will check the second to last, which is this pineapple looking letter with a ring inside it, which is an E, which matches up here. So I'd assume that's love water. Okay, so 2 questions left to go. Arrobots walk. An arrobot is a robot that can follow black lines drawn on a piece of paper. On every line, there is a label which tells it to turn left or right at the next junction. Some labels are already chosen, but there are still some labels left to choose. Jane wants to be able to start her arrobot at A, B, or C. She also wants her arrobot to always end up at the charging station. If the arrobot ends up at A, B, or C, it does not know how to continue and turns itself off. Help Jane finish labeling the lines so that the arrobot always ends up at the charging station. So the first thing we'd see that obviously once B comes down here, we want it to turn left. Okay, And over here with C, we'd want it to turn right. Okay, so this would come down this way and straight down this line. B would do the same. So we know those two are dealt with. A would come down this route as well. So once it's come down here, we need to make sure that A will also turn left. So now we know that every arrow would come down and come up this route here. So once up this route, we can either get it to go around this way, okay, or we can get it to come around this way. So I'm going to go with the right hand side, and that should get itself to the charging station. But obviously we need to get these two sorted as well. However, that should be sufficient. If a robot was to come this way, we would want to make sure it could turn left on this side, left on this side. And if it was to come back up here, instead of it to go around in a triangle, we'd get it to turn left again. So it could come back up like so. Okay, and it's always good to just run through. However, the only three we're all worried about is A, B, and C. So we can follow A, okay, so this one should be always coming up there. Following that way, coming back down there. And it will come back round and go in there. Okay, so that should work as well. So let's head over to arrows. In the figure above, the black arrow at A points at one black arrow at B and one white arrow at C. The white arrow at C points at exactly two white arrows. In the figure below, can you change the arrows from black to white or white to black by clicking on them? Your task is to create a set of arrows so that all of the white arrows point exactly at one other white arrow and all black arrows point at exactly two other black arrows. So all white at one other white and all black at one other black. So I'm going to start off here with one of these bottom corners because they are facing into the square, whereas these two here are only focusing in its line. So let's start off with this one. And as we can see, we've got three shapes there. One of them is pointing straight back. If that was to be black, then I could ensure that two of these would need to be black. And let's make those two black there. So now that I've got that, this arrow, these two should be black. And this arrow should have these two as black as well. This one here, that would work. This one here would need these two to be black as well. If that's the case, these two should be black, which is fine, that works. This should be pointing to two black. And now this pointing to two black, that works. This one should be pointed to two blacks as well. This one should be pointed to two blacks, which works. So now let's go through the whole square. This one pointing to one white, which works. This one white, which works. This one two blacks. This one two blacks. Two blacks, two blacks, two blacks, one white, two blacks, two blacks, two blacks, one white. One white, there's a problem there. One white, that works. One white, that there's a problem there. Two blacks. So we know that all of this is fine apart from these three. Now we know that these two are actually pointing to each other. If I was to make one of these black, then that would mean I would need two of these black, so that would work. However, I now have I have no whites for this one to point to. If I was to make this one black, then that would mean that these two would need to be black, and then we have too many shapes which are black. We'd need one white in there as well. However, I've got this one. If I was to change that, that would work in terms of black. That works in terms of white both ways. And there we go.